does everybody see my screen? Are we in good shape here?
Yes.
Muchas gracias, Irene.
My pleasure.
Yeah, mucho gusto. You know, with an introduction in which starts with a PhD thesis on the moon, you wonder how romantic this is going to be. Well, I'm back to Earth and working on very practical things in these days. Today's seminar is going to be best practices of geophysical characterization and seismic monitoring. And I have to thank Joseph Ireland and Sarah Blake for inviting me to give this seminar and the opportunity to talk to you. I wish it was not remote, and I wish I was speaking in your presence, but they would call it hands across the sea at the moment. The subtitle here is that much of the work I'm going to talk about, yes, I've been involved in, but there have been immense contributions from a variety of people who I'm calling the Friends of the Brittle Crust. And this will become pretty apparent what I mean by that as we talk through. In geothermal energy, the absolute critical thing is to have fractures, because unlike petroleum, this all depends on high flow rates. A liter of oil is 50 to 100 times more energy rich than a 100-degree drop of water in a geothermal system. So it's critical that we have this short circuit of, instead of permeable material, porous material that's permeable by the porosity, that we have fractured material that's permeable by actual pathways through the rock. So that's where this term brittle crust comes from. Okay, let's see if we can get this to move forward here. There we go. Okay. The reason for this view is illustrated very well in this photograph from New Zealand. It's a Greywacke outcrop of a hydrothermal circulation system, in which you very clearly see a main channel with a hematite center core and a limonite boundary. And if you're a geothermicist, this is where you want to drill. So much of my talk will be echoing back this idea where to drill. Sitting on the top surface with all the vegetation and all of that, finding this spot isn't easy. Moreover, there's a proliferation of smaller channels that you're going to see here that I'm pointing out, all of which contribute to the flow, but in fact are giving us a picture of a rather different view of the crust than a diffusive, porous medium in which the fluids flow in a front there. So the purpose of talking about fractures and the brittle crust is this issue of getting geothermal to flow at 50 times the rate that you have in a porous oil field, in which you can keep pumping and still get the energy equivalent of that liter, of those 50 liters in one. So I hope you can see here and not blocked by this camera. The theme here is, where are these fractures and how do you find them? So I've divided this discussion up into three parts, sort of after talking with Joe and Bob Rain and others and Sarah. I'm going to be looking at let's say, a past geophysical approach which makes use of earthquakes and the electrical resistance. I hope everybody can see my cursor here. And then I'm going to follow it with something far more relevant to the situation in Ireland. A profusion of earthquakes in Ireland would be a national bit of news, but in many hydrothermal systems, it's not. That's why this is going to be a short presentation here. But I'm going to follow this with something I think is really fundamentally important in Ireland, which is fracture seismic mapping using an ambient seismic method that doesn't require either earthquakes or a surface source like a vibroseis or dynamite system. We're going to also take a practical tour of where to drill channels form in rock and how, and what is the physical origin of these, and try to give a sense of what it is that guides our efforts to try and find those places to drill based on the nature of rock outside of a uniform medium. Well, we're going to finish up then with a kind of a request a bit from Sarah, because she heard a talk I gave in Iceland about controlling micro earthquakes, which is, of course, a major issue for all of us in the development of this, because we don't want to fall in the trap of having to abandon things like they did in Basel and unfortunately in Pohang in Korea, where at least one fatality was associated with that 5+ earthquake that took place there from a geothermal development of injection. Now, I was cautioned by Joseph and others that in addition to keeping it as simple as possible, I needed to avoid as much math as reasonable. And so I took to heart the following Calvin and Hobbes cartoon, where father says, oh yeah, what do you want to be when you grow up? Every job requires some math. That's not true. I'll be a geologist. That's not really a job. I love geology. I'm a seismologist, but I thoroughly agree with Calvin in this circumstance and with his father, because I love the whole discipline, and it's more fun than any other job I ever took. Okay, so let's look at this approach, this past approach, in which you're using earthquakes. Here on the left, you see a seismometer, a standalone one that has a sensor in the bottom of that can. And we put out 25 of these at Krafla, Iceland, and recorded several hundred earthquakes. At the same time, on the right there, you see 3 magnetotelluric devices that were used to map over 200 stations over the Krafla geothermal field, which you see in the background here. On the left is Stephen Onacha, a Kenyan, who was brilliantly put this together into a picture that I'm going to demonstrate here for you that is extremely useful. This was used by the United Nations and the World Bank in their best practices for geothermal exploration 20 more odd years ago. It depended on something called shear wave splitting, okay? This is taking the seismic S wave, and as it passes through a set of fractures, it experiences a response to the strength of the rock in 2 directions. So here's a set of fractures. Here's an S wave, a seismic S wave, which displaces the ground perpendicular to the direction it's moving up from a micro earthquake at the base here. And if you take a notebook and squeeze it perpendicular to the pages, it can collapse quite easily. Whereas if you squeeze it from the direction of the pages and the cover, it doesn't squeeze near as well. And so there's a difference in mechanical compliance here that is important. And what happens to the seismic S wave, because of the difference in the mechanics, it splits. There is a slow wave that's associated with the weak and a fast wave that's associated with the strong direction. And there's a time difference between them that depends on the density of the fractures and their mechanical properties, for example, the aperture of the opening. So we mapped at Krafla hundreds of these time differences and the orientation, the direction in which these 2 waves were coming. The fast direction is along the fractures and the slow direction was the perpendicular to them. We had an assistant who spent 6 months picking these directions and picking that time difference there. The same similar arrangement of fractures and resistance across these can be seen here, whereas the gaps in the rock create a resistance channel to flow, whereas along the channels, there is a significant amount of more current flow. And there's an orientation to this that can be measured by measuring the resistivity in 3 directions, in particular the 2 horizontal directions that would align with that. So what you noticed in the abstract was this idea of joint geophysical imaging. And here's a very practical result from exactly that, where the directions of the shear wave splitting, the fast direction being along the fractures, and the slow direction across them, aligns with the electrical resistivity. On the bottom here, you see the orientation in geographic terms, and then you see the number of split waves seen at this station versus the direction of the polarization there. And at this site, we have a maximum of a number of split waves and the direction of the polarization coinciding in both cases. Well, at this station, then it was drilled and it produced the largest producer, 40 megawatts at Krafla. So that's why this was thought to be best practices. We did this in California, we did this in Kenya, and it worked well, but it is sort of works where the where to drill is resolution is low. And it's certainly not practical in Ireland. It doesn't, micro earthquakes are not there, and some of the urban electrical effects are not conducive to this kind of thing. Instead, I want to bring up for your knowledge and I hope understanding and participation, because if you're doing seismic reflection profiling in any swath or 3D form, this is what I believe is the coming thing. You know, we've had 3 revolutions in seismology for exploration. First, there was refraction profiling. That was the 1920s, 30s, all the way to the 40s, where salt domes were looked at by refraction. Then came along the Vibroseis era from the late 1950s through to the present time, in which they expanded to the whole business of doing 3D seismic with thousands of channels of seismic. If you add 10% of time to those surveys in cost and time and record without any sources, just listening. Okay, I'm going to emphasize this. This is ambient seismic imaging. And this method works from, let's say, a few 100 meters in depth to a few kilometers in depth. And it does not depend on any active source, which I'll explain here in just a moment. Stress changes signals make fractures go into a vibrational mode that is very small. We're talking about minus magnitude earthquakes. I know that I always explain to my students that a negative magnitude earthquake isn't the absence of them, but they were just hundreds of times smaller than the smallest thing that Richter put on his scale at 0. His instrument couldn't see anything smaller than that because of the background noise on the instrument. So he said that anything 10 times that noise was a 1, 100 times was a 2, and so forth, a logarithmic scale. So a -1 is simply 1/10 of that. And by putting equipment in boreholes, we're able to record that, or then by listening for a very long time, we can do this. Here is a map view down, X position, Y position, on a place that has a fracture. And in this case, it happens to be a distant earthquake surface wave coming by. And what that initiates is a very, very small, but nonetheless measurable seismic signal on that fracture, resulting from the fact that there is a channel with fluid against a solid rock, and you get a signal called a Crowcless wave, which then progresses into a standing wave. The signals there that are in the loops around the fracture are actually scattered from that initial wave. But on the far right, what you see is a string bean, a rope of beans there that is actually a resonance standing on that fracture. Now, this is no surprise in volcanic seismology because that's exactly what we see. We see harmonic tremors. They're called tornillos, the word screw, meaning the shape of the signal coming from fractures in volcanic terrain. And if you listen long enough, because these last not seconds, but tens of seconds in the earth after they're disturbed, and you can make this disturbance by having a borehole and simply pumping some high pressure water into it, creating a strain change, causing the vibration in these. These are well established in laboratory and now well established in the field. So here's how it's done, and this is why this is relevant for our discussion here, is that in this cross section with depth, we've divided the Earth up into, in this case, what appear as pixels. And we're going to divide it up into voxels, meaning volume pixels. And you have receivers on the Earth's surface, a lot of receivers. And from these fractures, by listening long enough, in the initial method of doing this, listen for a week, and then use the stacking, meaning the summing of signals, to try and image the subsurface. Here you see a layout for a study area that's, let's say, 2 by 3 kilometers in map view. That's that blue patch there. You lay out seismometers with a buffer that's equal to the depth, 1.5 times the depth of this. So if we're having a buffer here of about 1 kilometer, that would mean we'd be looking at something about 750 meters down in the ground. That's sort of the optimal between, let's say, 500 meters and 3 kilometers is where this method really comes into its own. The blue are surface receivers. In this case, I'm showing out 2,220 receivers spaced on a hexagonal grid with spacings in between the receivers of sort of in the 50 to 70 type meters. If the reason for doing that many is to try and suppress surface noises, for example, a car driving by or a pump working there, if you go below the surface and get away from those surface noises and the signals that they generate, you can cut down the number of sensors immensely. And in this case, something like 74 buried sensors at like 100 meters. Not that this is cheap or straightforward to do. You can cut the number down and you can eliminate a massive amount of work trying to filter out noises. So here's a raw section from all of these thousands of channels. Time going down, channel number going across there. And it looks like a mismatch, but now you take the time differences between the arrivals, you know a velocity model, and you align it up. And if you look at that last image there on the bottom, what you see are actually seismic arrivals that are harmonic vibrations that relate through to the vibrations of that fracture. And I'm going to prove to you that this is actually so by actually doing, showing an experiment that was done in a shale application here. But what you do is you sum them all up and place them in a voxel, meaning a three-dimensional pixel here, by adding up. You see, I'm adding up time, and initially this was added up over days. We now know enough about this signal that we can add it up over minutes and expect to get some result. A typical survey might run for about 3 or 4 days, of which some 10% to 20% of the data would be identified as having these vibrations that I showed in the last image. And they're due to distant earthquakes, they're due to tectonics, they're due to tidal motions, they're due to strain fields. You know, look, the Earth is moving at a strain rate of 10 to the minus 4. That's 1 part in 10,000. That's what plate tectonic forces are moving the crust at. And as that strain is being built up, it gets released and moved. But on the far right corner, you'll see one of these full volumes where you see the bright spots. Those bright spots are where we will show you that those are in fact fractures. So the processing system looks like this. You got a block here, a volume. You clamp down to where you have the maximum, and then you skeletonize and pick the surface along which this system of signals is coming, and those are in fact the fractures themselves. This is the processing of ambient seismic data to image and find where to drill. So let's demonstrate this as true. Okay, so we're going to talk about a demonstration, yes, in Barnett Shale. This is an example of where data were recorded originally on a large channel, 2,500 channels. The bar on the lower right there is a kilometer. Okay, the red lines were produced by the process that I just showed you, collecting all the data, stacking it up, summing. In terms of reflection seismology, this is 500,000-fold of signal. And the red lines are what was the result of picking that connected surface along which there was a fracture, or to be a fracture, or a fracture system, a system enough that in fact it would respond not as one large fault like that, but in fact a series of fractures that when they were disturbed by a passing earthquake wave or a change in pressure in a well, that was that, you created this kind of a track. If you will, we're looking down along a set of curtains. We're up on the roof, the ceiling, and we're looking down on a window curtain. And this map is a cut through those window curtains, the curtains being vertical faults, fractures, fracture zones. Okay, and I'm going to show you now the equipment was left on the ground. The company wanted to do a test and see whether or not there was really signal coming from that location. So these features, which we called permeability fairways in those days, they're now just fracture seismic images. There was a lateral well drilled through here and pumped. And when P critical, which is the moment fluid starts flowing into these fractures, here's what happened. Here's the signal that was seen. Remember now that any pressure change in these fractures can cause a vibrational mode of the fracture. So let's look here. Okay, a little some signal right away when it starts flowing. Okay, that's the kilometer. That's a minute in, and that's there. Okay, let's run it again. Okay, so this is at the start of the flow of the pressure into that, but we can see that in about a few minutes, you have a signal coming out. In fact, it comes through very fast, something on the order of like a kilometer per second or so on that type of order to 10 seconds. What's unique about this is that, yeah, this was where the stimulation pressure was put on, but if you look, the first one that responds is way over here, more than a kilometer away. That's because these curtains intersect above and below this map. Moreover, at the end of this, you can tell that this is where you drill in order to drain this, and that system, but it has no effect over here. This is the second place you drill. You now have a direct map of where to drill. Applying this in geothermal, this is from New Mexico, okay? It is called the Lightning Dock Field. There's a couple of papers written about this, and we're looking at a map now here that's also in terms of depth, and the image here is at the high point of about 1,500 feet, meaning 500 meters or so in depth here. Like the previous one, we have a cloud. Remember, this is a cloud here where the darkest spots in the middle are the maximum amount of signal coming out. And here you see it in color where the red is the bright. This was done during a downtime in the geothermal field's production. And what you see, the bright red spot there in that center, that's in fact their most productive well. The point here was to try and find the next wells, where to drill, okay? And we can discuss this some further here in the future, but this was the map that was used to cite another production well drilling on there. The zoom on the right there is an expansion of this particular image, and it is known from other drilling and other imaging, seismic reflection, that in fact that's a fault zone there, and that these other places here are more isolated features in which there would be these kinds of fracture systems. So it has had now application in geothermal in the US. This is the second one. The other one was done in Nevada at the San Emidio fields there by Ian Warren. This was work done by a company called Zanskar. Joel Edwards and Carl Hoylen were the principal investigators here, and this was used to cite a well. So we're back here to this question as to can we understand this system in something of a broader context in terms of the mechanics of the crust like this? All geothermal flows in channels. This is a unique picture from quite deep in the lithosphere, where what you see is that there is a series of small channels that progress into connecting to a large one where the fluid flow was the maximum. And I want to stress here that there are two fracture systems. There's the exposed one where the extension joints are there. That's the one that goes all the way from the lower left to the upper right. But there's also a paleo one that stretches all the way from the right edge, lower quarter, right edge, all the way through to the left side. And this is really what is driving the creation of fluid channels, is this conglomeration of smaller channels that feed into a larger channel that take us back to this picture here. This has very important descriptions in the critical state of the crust, okay, put simply like that. On the opposite end of the scale, at the opposite end of the crust in terms of the surface, here's a photograph of an outcrop that illustrates exactly what I'm talking about. What you see here is a profusion of small fractures. Many of them, you can see the connection into a larger fracture, many of them feeding into this large fracture that goes from the upper surface to the down surface, where all the fluid has drained into and taken the iron and concentrated along this fracture. I always emphasize to my students that you can't put a picture like this up without a scale, because this scale could be a centimeter, it could be 10 centimeters, it could be a meter, it could be 10 meters. In fact, this whole picture is over a couple of meters. But in critical systems that are describing rock, there is a self-similarity in which the scaling goes down to the millimeter level of fractures, up to the kilometer scale, in which there will always be one feature, that feature in the center of this one, that spans the whole picture. Cut the picture into quarters, and you look over to your lower right quarter, there's another feature that goes the whole way. Cut that into quarters and take it to an eighth, and look at the lower right corner, you'll see that there's always one feature that goes all the way through. This is in physics called self-similarity. It has a very strong history in solid state physics. We won't go into, but I'm going to expose you to some of it here. And this is the math, okay? So we'll just be here. Look at this equation here. Those of you who suffered through optical mineralogy remember something called a Bragg vector. It's the number of spacings of mica layers per centimeter or millimeter or meter. Here, this says that if the spacing is large, 1 over the spacing is small. That means that the 1 over the, if this is large, this is small, that means that these spacings are very numerous here. That says the physical properties given by this are very much less than the ones that are spaced large apart. You can see it optically here. This color is very indicative. There's one of these spacings, maybe 2 per this 2 meter square. So the number per meter is small here. This number is small. 1 over that number is large. This is a rule known from solid state physics and critical state physics. It also leads to the following rule, which I prefer to look in this form, but let's talk about it here, that the change in porosity results a change in the logarithm, or better yet, down here, if this isn't blocked on your screen. Can everybody see that? There's an exponential here. That the permeability is related through the exponential power of the porosity. This is how fracking works. You increase the volume, the porosity, by a factor of 2, and you increase the permeability by a factor of 100. So how this plays out in our understanding and how we can model things like that is shown on this video here, where basically you have a model, a cross-section that's about 4 kilometers deep and something like about 8 kilometers along, 7 kilometers along. We're going to flow cold water in from the side here. Down at the bottom, you see a hot plate. And in here, we have put in a model term, a permeability that is related through to the exponential of a porosity. And their distributions are in terms of a normal distribution of pores, meaning a population of larger pores that have a bell-shaped curve, to a log normal where 1 or 2 main channels exist that go that. And what you're going to see now is the water flowing in from the side, getting heated, and going up one of these channels that's described by those relationships, meaning that the flow is dominantly in the channels and not in the pores. I'll run it again here, okay? It's in these channels, and we are learning how to model these kinds of flows and channels. So you see them here, and you'll actually see that the water can actually circulate hot and cold water through various channel connections that are not diffusive, but in fact are connected that way. And may I show you here, take a look at the distribution of the cloud of flow here and compare that to this. So this is where we're getting to by thinking about fractures, not permeable or equivalent porous media, but a fractured medium in which the dominant flow is along a few very large channels that are fed by a whole series of channels. Okay, I'm going to finish up here in honor of Sarah to tell you a little about how we avoided that horrible thing called induced earthquakes that stop a project. And this is the project in Finland where a 6-kilometer borehole was drilled. Here you see that's this test well OTN 3 down to a depth of 6 kilometers here in this granitic rock with only a cover of glacial till on top. There was an injection where 18,000 cubic meters were injected in 49 days into a set of stages here. Here's the cross-section of the well, and you can see that the S1 through S5 are the places in which the fluids were injected that was fresh water. It was drinkable water from the surrounding university's water system. And we used 2 seismic systems here. If you can see my cursor, you see I'm circling here a seismic array, a vertical seismic profiling of 12 geophones placed underground about halfway to this point here. It picked up magnitude -2 type earthquakes. There was also, for location purposes, in 350-meter holes, 12 stations in satellite surrounding this for location. And here what you see is a picture of about 1% of the earthquakes that were recorded by that system. The colors are associated with the sections where the injection was taking place. They were located with standard seismic methodologies. And the idea was to use the location and the physical characteristics of these earthquakes to try and control the size, the maximum size, while still obtaining a stimulation of opening up the fractures to allow geothermal fluids to flow. So I'm going to finish up my formal talk here with this diagram, and then a nice movie that I'm going to show you of an actual ambient seismic image of a fracture. But let's focus here. This plot is the ratio of the amount of earthquake energy emitted to the amount of energy being pumped in. You know, energy and work being done is equal to a force times the distance. Well, the pressure is a force divided by area. So the energy here times the volume of flow going in gives you a force times a length there. The volume divides out over the area, so you get a force times a distance. So that's the amount of work that the pump is doing by pumping fluid into the rock. Straight physics. Work is equal to force times distance. That's what energy is being pumped into the rock. That's elastically deforming the rock to the point where the strain gets to this number, 10 to the -4, and an earthquake is produced. Now, if you take the energy that that earthquake generates or emits, radiates, and put a ratio over it, that's what this I efficiency is. Okay, and it's a small number because it's parts in thousands here, but the amount of work going in, starting at the that when you start putting work in, yeah, the earthquakes start going off and you start getting small earthquakes radiating, but it settled down into a constant rate. In other words, as you were pumping into the rock, doing the work pumping in, the amount of earthquake radiation was a steady amount. It stayed at this ratio of the amount of energy being that, meaning energy was not accumulating. But in phase two, the pumping and volume went up, the work, the amount of elastic distortion went up, and we started to having more radiation coming out, meaning bigger earthquakes. And at one point, we got very close to the cutoff limit that was being allowed for this. That was a 1.9 event in the limit of 2.1. And we stopped the pumping, we stopped the working, and went back to a more modest pumping rate, where the work being done, the pressure times the volume being injected, and the ratio of the earthquakes became stable again. And we were able to pump for the total of the 49 days, injecting 18,000 cubic meters of water and not creating a Basel, a Pohang, or other disasters that would have stopped this project dead in its tracks. So let me just show you what an actual fracture looks like, a frac. Where is it making open fractures here? This is a map view looking down. You see a drill hole that's going from the upper left to the lower right. You see some colored sections there. Those are perforations in which the pumping stimulation injection of fluid takes place. This one is embedded in this ambient seismic image. There is no other source, no explosion, no vibrosize. This is a large channel system sitting on the surface, listening for where the fluids are creating a vibrational system in the fractures. And I'm going to run a movie here so you can look around and see the complexity of these fractures. This is about 120 meters across. We're looking down. Now we're going to go into the earth and look in the horizontal. Follow the fracture surfaces along, and you can see the complexity. On all of those surfaces, there was a cropless wave causing a modal vibration of the fracture itself there. Well, if I had a little more foresight, I would have called this linking fluid flow, microearthquakes, and fracture seismic imaging in the brittle crust. I thank you for your attention and the honor and privilege to speak with you today. I hope that I've piqued your enough interest that someday you invite me to join you.